And while we're solving the problem, we're going to update our little picture over here with the magnets. And I'm going to draw a half-life. You can kind of see I did it earlier. We're going to draw a half-life graph too. So we're going to do three things at once. So write this question down. Here we go. A 100-gram sample of carbon-14 decays, sorry, that's a Y, decays for 22,860 years. How many grams of carbon-14 remain unchanged? So go ahead, copy that down, please. A 100-gram sample of carbon-14 decays for 22,860 years. How many grams of carbon-14 remain unchanged? So I'm going to show you the method that I use to teach it, and it is very helpful when you're first learning it. In the lab, we are going to do more practice problems. I'm only doing one right now in class, and then we're going to move on. But in lab, we're going to be doing a couple worksheets with just a bunch of these practice problems. So once you get good at it, you don't have to use my technique, but I want you to at first. All right, so right here, we're acting as if nothing has happened yet. We have a brand new sample of carbon-14. Has not decayed at all yet. Okay, when it does decay, this is what happens. It decays into nitrogen, emitting a beta. That's what table N tells me. And it takes this long for half of them to do it. So here's what we do. We set up a chart. So do this in your notes, please. This top one is mass, top left. Middle is time, and this one is half-life. And actually, did this morning. We're going to do another one here, over here. One more. Sorry. Just extend that a little bit. This is going to be nitrogen 6. Nope. Nitrogen 14. Mass. So this mass over here is carbon-14. That mass over there is the nitrogen 14. So, half-life questions, very common on the regents. This is how we do them. Set up a little chart, mass, time, half-life. Mass, time, half-life. We're going to do a lot in lab, so if you don't pick it up today, that's okay. You will have a worksheet due tomorrow where there's one problem like this. The other ones are kind of review. I'll make sure everyone's ready before I move forward here. I think I left the water over there. Thirsty. That's unfortunate. All right. We all got the chart ready to go? Okay. Here's the most important part of the chart. Once you have it set up, we always put 0 here, 0 here. 0 for time, 0 for half-life. What does that mean? Look up here. It means this. It's all carbon-14. It has not decayed at all. We act as if time hasn't started. That makes no sense in real life because time is always moving. But on paper, to do this problem, we assume time hasn't started yet. So therefore, it hasn't gone through any half-lives yet. So if you read the question again, what's the mass we should put right here? But nothing has happened yet. 100 grams. So 100 grams are still present. It hasn't decayed yet. This is real important. You follow me, pay attention, ask questions. First time you see this is the most helpful. Or it could hurt you the most if you really aren't paying attention. So you always start with the mass that they give you and then 0, 0. Okay, so that's where we are here. We have 100 grams of the carbon-14. So now what do? We go to table N, we look up the half-life. We did that. 5,715 years. Okay. After one half-life, what do we put in time?
5,708.
Very good. 5,715 years. Now, who can tell me what mass do we have? 50. Very good. That's what half-life means. Half of the mass will decay in that amount of time. So, just to go slow here with you guys, I'm going to go through the magnets again. So half of these, so 8 of them, will decay. So I'll take random 8. Remember, it's not always the same, it's not always a group. It's kind of random. So what do the yellow ones represent? What's the yellow ones?
Nitrogen.
Nitrogen 14, right. So I want to show you what's interesting. After one half-life, 1, 2, 3, 4, 5, 6, we'll go 7, and we'll do this one, 8. Okay, so after one half-life, who can tell me what's the ratio of carbon to nitrogen? 1 to 1, very good. So we have 0 nitrogen, I forgot to fill that in, sorry. 0 nitrogen to start, right? 0 nitrogen to start, all carbon. As it decays, half of it will now be over here. You know what, I'll use red. Maybe it'll help you see it a little bit easier. So notice after one half-life, where did those 50 grams go? They didn't disappear, they transmutated into nitrogen. They transmutated. So our little picture here is half and half. All right, we didn't answer the question yet. Here's why. 22,860. We're only at 5,715. So we keep filling in our chart until we reach that number. And I get it. Some of you pick this up quick. There is a shorter way to do it. But I like to do this to show everybody the concept, the process. So basically I'm saying do what I'm doing. 2 half-lives. How much time has passed? Who can answer that?
11,430 years.
Very good, 11,430 years. Jake, how did we get that? How did we get that number?
Just multiply the first one by 2.
We added, I'm just going to say it differently, but you're right. We added 5,715 to 5,715. Why? Because another half-life passed. How long is that? 5,715. Who can tell me what mass remains now? 25. Very good. 25 grams. How much N14 do we have? 75. Whatever the carbon loses, nitrogen gains. That's the concept here. So we have 25 and 75. And I have to take away how many of the green ones? How many green ones turn yellow now? There's 1, 2, 3, 4, 5, 6, 7, 8. So 4. 4 of them now have turned to nitrogen 14. Again, it's kind of random. It doesn't matter where I take them from. Okay? So notice what's happening is the ratio is changing. 1 to 1. I think you answered this last week, right? 1 to 3. I think that was you. A 1 to 3 ratio. We're not there yet. We're halfway there, right? That number's half of that. So after 3 half-lives, how much time has passed? 17,145 years. That's not right? Or that is right?
It is right. She used calculators. She has her phone.
Just, there's no reason for your comment. Stop. So you add the half-life here. Who can tell me what's the mass remaining?
12.5.
Good. Half of 25 is 12.5. What about nitrogen?
87.5.
Say again? 87.5. Very good. Very good. And again, I'm going to stop writing the numbers so I'm running out of room. But again, 2 of these now would become yellow. Notice what's happening. Eventually, we'll get down where there's only 1 atom of carbon left. The thing is, though, let's say this is made of carbon-14. This is made of trillions and trillions of atoms. So this is only a 16. So I'm only showing you 16 atoms as an example with the magnets. If this is made of trillions and trillions, it's going to take a long time to get down to 1 atom, right? So, and you can't have half an atom. So it's either 1 atom or no atoms. So that's why your half-life graph, which I'll draw, will never really reach that x-axis. It'll start to kind of level off, but it'll never really reach it. And just because there's so many atoms, and it won't just disappear. It can't. You can't have half an atom. Anyways, just notice that. Okay, your nitrogen is going to increase, your carbon's decreasing. And what about here? 4 time after 4?
22,000.
Yeah. 22,860 years. So that's our end. That's our ending point. That's where we stop. What's the mass of carbon 14 remaining? 6.25. So that is the answer to this question. That's how many grams remain after that much time. And if we wanted to figure out nitrogen, we would have to add 6.25. So what is that? 93.75. I'll tell you right now, the Regents is never going to ask you nitrogen. Why did I show you? So you really understand what's happening. We're not going to just do questions just to get them right on the test. That's not how I do things. I want you to understand what's happening. So this is not going to be on the test or a quiz or anything that you ever see, but I want you to understand the concept, okay? So the carbon doesn't disappear, it turns into nitrogen. So that comes just to kind of increase our understanding. This, though, this chart is to help you answer the question, okay? So 6.25 grams. Now, the half-life graph, and you can just really watch, you don't have to sketch this. If we started with 100, and then we ended up halfway, let's say, is 50, another half is 25, another half is 12.5, another half is 6.25. So what we would do is we would graph this, and we would see that every time this split in half, what would it show on the graph? Who just did the left? What's this supposed to be on the x? We did trial and pennies, but what's this really supposed to be?
Years.
Right, time, right? So this is time. So this would be 5,715, 11,430, right? Yep. This would be 17,145. This would be 22,860. I know I'm getting messy. But basically, the whole point of a half-life graph is so you can see the mass will decrease by half as the time goes up by the half-life, whatever that half-life is. So that's why the graphs always look the same. It's just the numbers might change. We could start with 1,000,000. We could start with 1. And it depends on the isotope and the half-life, and that changes the time. But they're all going to look the same. All right? So I didn't ask for a whole lot of questions. I just really wanted to make sure I got all this down today so you had a concept of the type of question you'll see and how to answer it. So I'll stop for a second. Does anybody have questions on the graph, the chart, or any of that business over there? Any questions you want to ask? So this is typical, but they get a little harder. And in lab, we're going to see all the hard questions. All right, we're gonna call it today with the nuclear. I still have some time. We're going to start solutions, but I really want to make sure we got that. So no questions with this. All right, I'm going to clear it off here. Go to table F. Go to table F.
No, I'm done.
Just keep it. Just keep it. Do it at the end of class.
Yeah, this is money.
The end of class.
I don't think you can. There'd just be water. You would not make it. No, you wouldn't. Whatsoever. Like I was splashing.
Okay, title in your notes, solutions.
Oh, another spot.
Go to table F, please. You should know how to read table F already. Yeah, you've been working with table F. So table F I'm not going to teach you about anymore. I'm just making you aware that it is a solution chart. So when we say solutions, table F is part of it. So if you're still confused with table F, you don't know how to use it and say what's soluble, what's insoluble, come see me. Or I think Taylor's a pretty good expert at this one, right? We are going to briefly talk about F down the road, but we already kind of did a lot with that. Table G, on the other hand, is new. So flip it, go to table G.
Why didn't you just tell us in the first place?
Because I'm explaining table F as part of this unit, but we've already established that, hopefully. Table G.
This looks really confusing.
Which is why you're going to take a minute when I say go ahead. And you're going to look at it and really try and figure it out without me telling you, because you probably have heard other teachers tell you this, but throughout life you're going to encounter problems and situations that you don't know the answers to yet. You have to figure it out. Take what you know and figure it out. So, take a minute right now, try and figure it out. What is that trying to show you?
I already got it. You know exactly what it is.
All right, enough. We don't need the commentary. Shh. Stop. If you throw that to him or throw it out, I'm writing you up.
No, we're talking about this.
Okay, good.
Jeez. You're like ready to.
Look at all the lines, look at the y-axis, look at the parentheses of the y-axis, look at the x-axis. Notice how some lines are going up, some lines are going down. Some lines stop. In other words, at not at all temperatures can you see all the lines on there. All right, that was 1 minute. Who wants to tell me what this chart is showing us? Someone besides Ryan or Jake.
I haven't gone to it.
Yeah, he hasn't gone.
You've been helping a lot up here. Who's gonna be? Jenny, what do you think?
I think it shows like the different, like for each different thing, the line is showing if the solubility decreases or increases as the temperature goes up.
Perfect. Very good, Jenny. That's the main idea I want you to get out of this chart. Good job. Very good. So, which substance, or salt they're called, which salt or which substance does the solubility increase or decrease when temperature goes up? That's one thing I want you to be able to read. So 3 of those lines, the solubility actually goes down as it gets warmer. Which 3 lines are those? HCl, SO2, and H3. Right, those 3 actually go down. Everybody else goes up. First of all, let's make sure we understand what does the word solubility mean to you right now. Because I haven't really told you fully what it means, but you should already have a good idea.
Liquid.
No.
That's what it means.
Dissolves in liquid.
If it's an opinion, it can be wrong, right? An opinions can be
Yeah.
wrong.
But
So what does it mean?
Dissolves in liquid.
Dissolves in water mostly, but liquid, yeah. So if something dissolves, that means it has a certain solubility. But let's pick a temperature, let's say 20 degrees Celsius. There is one substance on that chart that has a much higher solubility than anybody else. Don't say it. One substance on this chart has a much higher solubility than everybody else on this chart at 20 degrees Celsius. Can you guys pick out the one at 20 degrees Celsius that has a much higher solubility than any other compound on this chart?
Why is it so much harder?
Xavier, what do you think? Yeah, Ki. Ki solubility at 20 degrees is like 145 grams. What does that mean? Look at the y-axis. Grams of solute per 100 grams of water. So what I'm going to do, because it's hard to just explain this out loud, I mean I can, but I'll show you tomorrow. I'll measure out 100 grams of water and I'll show you how much that is. I'll measure out, if I have enough Ki, I don't think I do, but if I have enough, I'll measure out 145 grams and I'll show you what that means. So I'm going to kind of show you some of these just to give you an idea of what this is talking about. But basically it means how many grams, almost done, but stay with me, how many grams of each of these can you dissolve in only 100 grams of water? 100 grams of water, if I had a beaker, is like maybe like that much. Okay, it's a very little amount of water. So some of them you can dissolve a lot and some of them you can't. But notice, if you increase the temperature, what does it do to almost all of these?
increase
It increases what?
the amount that you can dissolve.
Right, it increases the amount you can dissolve. That's called solubility. It increases the solubility of these salts or of these compounds. So the last thing I'm going to get into here, and we'll write it down, is when we're talking about solutions, let's write this down, there's 2 parts to a solution. What are they? So you want to make salt water solution. Take salt, take some water, mix them, stir it up, salt dissolves, you have a solution. What are the 2 parts of that solution?
Water.
The water and the salt. What are they called?
The solution
H2O.
of this.
The what?
The solvent.
Solvent and the
Solute.
solute. Very good. You have the solute and the solvent. So if we're talking about salt water, the solute would be the salt, NaCl, solid, and then the solvent would be the H2O, liquid. And if they come together to make a solution, what's the symbol for that? Aqueous, good. NaCl, AQ. So anytime you see AQ, that means solution, and there's always two parts, the solute and the solvent. And I'm just going to add one more thing. This is usually a smaller amount, and this is usually a larger amount. In other words, the water volume will be much greater than the amount of salt you add. Imagine taking a drop of water and putting it into a giant bucket of salt. That water won't dissolve the salt, right? So that's what I mean. All right, we'll stop there. We'll pick up with that stuff tomorrow.
Can I shoot it up? Right here.
No.
Why not?